So for this video, we're going to talk about the other type of mechanical resonance with regards to music, and that is your wind instruments, otherwise known as closed air column resonance. So in this example, we're just going to talk about how you can force air out one end of a tube, if you will. So every single one of these instruments, the baritone, the tuba, the saxophone, French horn, I'm going to call that a yak horn, flutes, clarinets, trombones, etc. You're forcing air out one end. There's other valves for air to escape, but if we're just going to be super simple about it, we're just going to talk about forcing air out a single end. You can get into the nitty gritty details as how it's different when you have, like for instance, the saxophone, all these different places where air can escape and how that'll actually change the frequency of sound that you'll hear. So what you're getting out of this video is fairly simplistic in comparison to what's happening in other cases. The trombone is probably one of the simplest ones where you can actually change the length of the instrument as you play it. But there's other types of closed air columns that's probably not as obvious. And you might be able to just do them by going through the fine water goblets that you might have at home, if you have any at home at all. But I don't know how well this is going to turn up on YouTube, but I'll just play this as an example where you have these two folks. I think they're called Glass Duo, playing, well, just, you'll see. I'll stop it there. So what you can see is they have all these water goblets that are all different sizes. You got the really tiny ones over by the lady here that are really nice and small, and they're providing really high frequencies. And the fella here is playing really big ones that have some water in them, of course, and they're playing low frequencies. So you might be able to do this at home if you can fill them full of water and just wet your finger and rub your finger along the top, and you can create resonance. Um, I'll just minimize that. Hopefully that turns out okay on YouTube. And if not, oh well, look it up. I'll see if I can put a link for it down below. So those are just examples of closed air columns. In fact, the lab that you're going to do in class, and if not, the lab that you're going to probably watch me do in a different video, uses a closed air column to find resonance, and you can kind of have an idea of how to use that to calculate the speed of sound. Of course, using resonance. So these are closed air columns, so they're open at one end. The vibration is only truly able to escape out the one end, and so the physical structure is a little bit different than open at both ends, where you would have, where you saw a different case of that in the previous video. So all wind instruments are considered to be closed air columns. So when you put your mouth on it, like on the trumpet, for instance, I'll just quickly see if I can draw it. So you got the spigots, and then you've got your trumpet. Sure, that's an instrument. There you go, terrible mouse drawing. But when you put your mouth on there, you blow air so it only goes in one direction. Okay, so that's the whole, even though it's technically open here and here, when you put your mouth on it, you force air out only in one direction. So that's why we can still call it a closed air column. Air is not escaping back out the other way like it would with open air columns. So as far as the actual waveform and what the structure looks like, just like where you had an open air column, you want the air escaping at a maximum. So maximum crest, maximum trough, or of course, since it is a sound wave, we know it's a compression and a rarefaction. Just crests and troughs are a lot easier to draw. So when you force air out, you're creating a node. And again, if we're talking about like a trumpet, right on the mouthpiece where you're forcing the air in one direction. So in this case, if you look at the actual structure of a wave, so we have a rough crest and a trough there as best as I can draw it. We're not getting the full wave whatsoever. All right, if I divide this into quarters, so starting from this orange marker, there's the first quarter of the wave, there's the halfway point, there's the next quarter, and there's the end point. So what we're getting is just 1/4 of the actual wavelength, escaping out the fundamental. So just this much of the wave is coming out. So of course, as it's going back and forth, it creates these loops. So if I loop that in there, there we go. There we go. You're basically just getting this little section here, and that's only 1/4 of the wavelength, right? So 1/4 of the wavelength is coming out. So that basically means that the length of this instrument, so at the fundamental mode, the very lowest frequency that this thing will allow sound to produce is going to actually be 1/4 of the wavelength of sound. So in the string instruments and the open at both end instruments, the fundamental was different. The fundamental was half a wavelength of sound. So this one is, it's not like the other two. So the other two are mathematically identical, even though physically something different was happening. This one is physically different as well as mathematically different. So sometimes it trips up some students because they're used to using the other equation, but closed air columns, we have to do it a little bit differently. So if you can get it to, if you can force it to vibrate with higher frequencies, the next overtone up, so that's N value number 1, in order to get the wave to exit with a maximum. So again, we're always going to have it to exit at a maximum. So we're always going to keep on this 1/4 of the wavelength. So the fundamental sticks with us. But between each overtone, you want the node to always be at the closed end. So you're going to add on another half a wavelength of sound. So if you add them together, 1/2 and 1/4, the length of this instrument is just going to be, so 1/2 and 1/4, of course, is 3/4 of a wavelength of sound. All right, so we got 1/2 a wavelength from there, there's your crest, 1 full crest, and then 1/2 a crest creates 3/4 of a wavelength. All right, the next overtone up, same idea. From where we left off, we add on yet another 1/2 a wavelength. All right, so if you add on 1/2 a wavelength and 1/2 a wavelength and 1/4 of a wavelength, you end up with the length of this instrument. So again, the length of the instrument starting from the left side to the right side, that's the whole length. From there to there, the length of the instrument is therefore going to be equal to 5/4 lambda. And then you probably notice a pattern starting off with 1/4, then 3/4, then 5/4, and the third overtone would probably be 7/4, and the fourth overtone would be 9/4. So we keep on adding on 1/2 a wavelength to after every overtone. Right, just to go to the next overtone, we're always adding on 1/2 a wavelength. So if we wanted to create an equation to satisfy any overtone value, we would start off with just recognizing that the fundamental, so again, the lowest frequency, is going to relate the instrument to be 1/4 of the wavelength of sound. Then, in order to go on to the next overtone, you just have to add on 1/2 a wavelength, every single overtone. So starting off with that, you create a fraction. So lambda over 1/4 plus over 4 plus lambda over 2 multiplied by the number of overtones, find a common denominator, and then you just group it all together. So as you can see for this one, we have a different equation than the other two, than the string instrument and the open at both ends. So I'll just put that equation on here. For that one, it was n plus 1 all divided by 2 multiplied by the wavelength lambda. So the two equations are quite a bit different. All right, so this tends to be some of the biggest problems when doing resonance problems. Some students will use the wrong equation. So I cannot stress this enough. Make sure you know which equation you're using before you do any of the math. Okay, so speaking of which, let's do the math. Suppose you have a trumpet. I basically expect you guys to know very simple instruments like trumpets, saxophones. I would expect you to know that a guitar would be a string instrument. Like I'd expect you to know a saxophone, we would force air through it. Same thing with a recorder or a flute. Other things like organ pipes and bassoons, those are a little bit more obscure. I wouldn't expect you to automatically know that it's going to be open at both ends, or even just what a didgeridoo is. But things like trumpets and saxophones and violins, I think are pretty obvious for North America to know what kind of apparatus it is as far as resonance is concerned. So on that note, back to this question. It says if a trumpet were straightened out, it would be about 2.65 meters long. Um, I'm sure that's an approximation. I know there's lots of different types of trumpets out there. I'm sticking with this random example, and if it's slightly out, well, I'll just shrug my shoulders. So if the speed of sound in air is 340 meters per second, what pitch is its fourth overtone? Start off with what we know. We know the length is 2.65 in this scenario. We know the overtone N is 4. We know the speed of the sound wave is 340 meters per second. We're going to use two significant figures for that because I didn't see an underline under the 0. And two significant figures is probably good enough. The frequency is what we're looking for. It doesn't say frequency, it says pitch. In the world of music, pitch is frequency. We'd like to use frequency for physics. Pitch would be something more for music aficionados. So since we know we're looking for frequency, then we're going to have to use the universal wave equation. The problem with that is we don't know lambda. We know the length, but that's not lambda. So I'll pre-manipulate the equation just so I'm ready to go after I figure out what lambda is. So the frequency of the wave is, of course, speed divided by lambda. So now I just need to apply the actual resonance equation. So the resonance equation says, since I know it's an open at one end, so closed at the other, it's a trumpet. So 2n plus 1 to all divided by 4. So I'll just have to put this 4 in place. So 2 times 4 plus 1 is equal to 265. Oh, sorry, multiplied by lambda is equal to 265. 2 times 4 is 8, plus 1 is 9. 9 divided by 4, 2.25, and then you just divide both sides by 2.25. So there's no units here. And as far as significant figures are concerned, none of these numbers here are significant. So I wouldn't worry about sig figs for this type of question. All right, I would look at the number given here and go, okay, 2.65 is the only measured number. The rest of these are just either part of the equation or else they're a counted number. So when that's the case, those significant figures don't matter. You can just take them at face value. So divide both sides by 2.25 and you should get approximately 1.17 repeating. That's what I'll carry forward in my next part of the equation because I'm not done yet. So I'll just put that in there as is for whatever's in your calculator. So you just take your speed of the sound wave divided by 1.17 repeating, and you'll get to two significant figures, approximately 2.90. So 290, not 2.90, 290 hertz. So tripping up while I'm talking today, apparently. That's basically how you do a problem like this. Not every problem is going to be a problem where you're going to find the frequency or the speed. Some of the problems are a lot more straightforward where you're just looking for relating the length of the instrument to the wavelength of sound. So don't feel like you have to do this for every single problem that you're going to have to do in the near future. As far as your assignment's concerned, do this one. Closed air column or open at one end. So again, it does have two names. Question 1 is very similar to the other two assignments for the other two resonance problems, where you're just trying to relate the length of the instrument to the wavelength of sound. So you want to find the relationship. Length is equal to some fraction, which I'll put a question mark here, multiplied by lambda. So that just all depends on whatever the fundamental 5th overtone or some 27th overtone is. So that's all you're doing for number 1. You're just creating an equation relating the length to the wavelength. After that, you're actually looking for numerical values. So I think there's 5 questions, maybe 7. I don't quite remember. I just did a screen capture, cut it off after this. So give it a go. And if you have questions, just fire me an email.